Hi everyone, welcome back, and let's start with section 5.3. We spent a lot of time previously talking about the first derivative and what we can do with it. Now let's talk about other derivatives, higher derivatives, second, third, fourth, and so on, and what we can do with the second derivative in particular, because it each has a meaning. Why would we want to do that, for example? Well, let's say if we have velocity, which is a rate of change of distance or position function, what if we would want to know how much velocity is changing? How much velocity is increasing or decreasing, for example? Well, if we take the derivative of velocity and keep track of how much velocity is changing, then it's known as acceleration, which is actually the second derivative of position or distance function. So that's how it works. Actually, you take derivative one at a time. You take the first derivative, then second, and so on. So second derivative, we'll look at it. It looks like f double prime of x, or sometimes it looks sort of like an exponent, like the 2 on the top. But basically, it means you take derivative twice. That's what it means. It's not really an exponent. Or how here you have the d, again, it looks like a square, but it's really just a second derivative of f of x. So to take second derivative, we simply need to take the derivative the first time, and then we take the derivative again. And then we can keep repeating the process as often as needed. So we can have third derivative. Notice we have f triple prime of x. Fourth derivative, now we stop with a prime, so we actually can put a 4 in parentheses to distinguish from exponents, for example. And there are also some applications with second derivative, and definitely a lot of significance with that we will see. Okay, so let's first work on taking the second derivative for a function. For polynomials, it's relatively simple, but we'll also take a look at some more challenging problems that will be on your homework a little bit later. So here's the goal. We want to find f double prime of x, then find f double prime of 0 and f double prime of 2. So how would we do this for this function, 5x cubed minus 7x squared plus 4x plus 3? Well, let's first find first derivative, which is 15x squared minus 14x plus 4. Then we must take derivative of that. So second derivative would be 30x minus 14. And now that we're done, we can simply plug in 0 and 2 to find the answers. So 0 would give us negative 14, and 2 would give us 60 minus 14, which is 46. So it's that simple for polynomials, but of course things get more challenging, as we say, if we have something more complicated. Let's say a rational function. We learned how to take derivative of this using quotient rule in the previous chapter, which for first derivative, that's what we can do. So let's try that. If you recall, for quotient rule, I usually start with denominator and square it. So it would be 1 plus x squared. Then, for the numerator, I start with derivative of the top, which is 2x, times the bottom, which is 1 plus x, minus derivative of the bottom, which is just 1, times the top, which is x squared. Then we can distribute and collect like terms. So notice we'll get 2x plus 1x squared, because the x squareds combine, over 1 plus x squared. Now, the challenge would be to take the derivative of this function to find the second derivative. Here we must use not only the quotient rule, but we should also use chain rule for the bottom function because it's an exponent. So let's see how that works. I've done it a little bit in the last section, but notice it's kind of a similar idea here. The denominator, remember, square of a square is actually 4th power, so that's how come I got that. Then what I did was I took the derivative of the top, which if you recall was 2x plus x squared, so we'll get 2 plus 2x times the bottom, original bottom, which was 1 plus x squared, exactly as is. Then minus, let's attempt to take the derivative of 1 plus x squared using chain rule, which would be the 2 would come down, that's how come we have this 2 here, times 1 plus x, times the derivative of the inside, which is just simply 1 here, but I'm putting it here in case it was not 1, for example, times the original top function, which is 2x plus x squared. So it looks like a big mess, but we can simplify this a little bit. If we take out 1 plus x, notice how it is in common with these two. We can factor it out, literally. And then what we have on the inside is 2 plus 2x. Then 1 of 1 plus x remains. And then we have minus 2 times 2x plus x squared. So notice 1 plus x was gone. And to do this, so we can cancel 1 plus x on the front. And we have 3 of them left over in denominator. And we can combine the rest of the terms. I used FOIL on the first two. So I get 2 times 2x plus another 2x and then plus 2x squared. And then here we distribute the 2, which is minus 4x minus 2x squared. And now notice what's happening here is the 2x and the 2x plus 2x would give us 4x minus 4x. That would be gone. And then 2x squared is gone with a negative 2x squared. So notice how we just end up with a 2 times 1 plus x cubed. So this was a lot of work for this function, but you should really practice because some of these definitely come up a lot. Again, the trick was to write everything out, but then we factored 1 plus x out. So usually one of the factors will cancel its denominator and makes things easier. So even though it looks difficult, it's still doable if you just keep going. And now we can simply plug in a 0, which we get 2. Let me scroll down a little bit. And we can plug in 2, so we'll get 2 over 3 cubed, which is 2 over 27. So this is how we do it for rational functions. Okay, let's keep moving. What about radicals? Square root of x squared plus 4. Well, if you think about how to do this for first derivative, again, we learned this already. We can write it as power of 1/2. Okay, now notice, be careful, you cannot actually simplify this, so do not attempt to take the square root because of the plus. Okay, so how to take the derivative? Well, it would simply be chain rule, so 1/2 comes down, times x squared plus 4. We subtract the 1, that's how come we get negative 1/2, times the derivative of the inside, which is simply 2x, and the 4 goes away. So notice I did get rid of the 2 right here, and the 2 right here, which is how come we end up with x squared plus 4 to the negative 1/2 power times just x. There is a reason why I kept it as a product, because to take the derivative of this again as a product turned out to be a lot easier than as a quotient. And I tried quotient rule in class. Some of the students tried and we couldn't quite get it. It was more challenging. But anyway, let's try this as a product rule. So let's say x squared plus 4 to the negative 1/2 power is f of x, the first function, and x is the second function. So let's use product rule on this. So again, product rule, the way it states, we got to take the derivative of the first function, which again is chain rule. So notice it's negative 1/2. This is actually a negative right here. Times x squared plus 4. Again, we subtract the 1, so that's negative 3/2. Times derivative of the inside again, which is 2x. And times the original g of x, so that's x, so the original second function. So this is the first part. That's probably the most difficult one. But again, we just use chain rule on all of this times x. Then the second part is easier. We just keep the first function the same times derivative of x, which is just 1. So that's how it works. Now the problem is to simplify this because we want to end up with a single expression here. And I know in the homework it's already simplified, so I'm going to show you this part. So how do we do this? We had the negative on the front, if you notice, so there's a negative. Then I just multiplied 2x times x. That's how come I got 2x squared. There is a 2 in denominator. And I simply put x squared plus 4 to the positive 3/2 power in the denominator. And the only thing is I cancel the 2's once I've done all that. Plus, the second part is a lot easier. The 1 was on the top, and the x squared plus 4 to the positive 1/2 now goes in the denominator. So we have this, so far so good, but we still need a single expression. So what do? Here's the tricky part. So this is the simplified version where I already canceled the 2. The tricky part is how do we bring this to common denominator? You have to think really hard because of fractional exponents, but the idea is it's already x squared plus 4, but to get from the 1/2 to the 3/2, what can you add to it? Because remember, when we multiply, we actually add exponents. Well, it turns out that 1/2 plus 1, notice how I wrote this out here, is 1/2 plus 2 over 2. It will give us 3 over 2. So if you learn this trick, we can just multiply x squared plus 4 to the 1 power on top and the bottom, just like with common denominators. Then we can finish this problem. So what we're going to have is we're going to have x squared plus 4 to the 3/2 power on both denominators, which will combine into 1. And on the top here, we'll have negative x squared. I just put the negative on the x squared, plus 1 times x squared plus 4. That's just x squared plus 4. So note the x squareds cancel. So we end up with 4 over x squared plus 4 to the 3/2 power. This is the single expression that we end up with, and you'll see it on View It example in my math lab too, for something similar. So yes, it was challenging, but we used chain rule to begin with, then we used product rule, including the chain rule, then we made them the same denominator by multiplying it to the first power, and then we ended up with this. And even more challenging, to plug in the 0. Well, 0 actually wasn't too bad. You'll have 4 over 4 to the 3/2. The way I think of 3/2 is a half power is a square root. So square root of 4 is 2, and then 2 cubed, that's 8. So we had 1/2 at the end, 4 over 8, which is 1/2. What was more challenging was when we had 2 squared plus 4. So that's 8 to the 3/2. Square root of 8 is not that simple, but you can pull out the 2. That's square root of 4 times 2, so that's 2 square root of 2 cubed. Notice how I wrote this out to keep track of. So we'll have 2 times 2 times 2. That's how come we end up with 8. Then you have 3 square root of 2's, which I have right here. But if you recall, square root of 2 times square root of 2, that's just 2. Square root will cancel out. So that's how come we end up with 8 times 2, that's 16, times square root of 2. So that goes in the denominator. I prefer to write it out earlier. And we can reduce the 4's, so you end up with 1 over 4 square root of 2. So a little lengthy there, but it's doable. And one more example. I'll probably make a separate video for the rest of the section. So there's going to be a 2-part video. I don't want to make it too long for you guys. So this is going to be the first part. And then I'll make the second part right after this. So to finish this up, one more example. If you have ln of x over 4x, when I did this problem for the first time, I actually kept 4x as a denominator. But that becomes a big mess with 4's floating around everywhere. It was just becoming a nightmare. So whenever you have a constant like this, you can actually pull this out, and then it becomes not too bad. Then you just have ln of x over x. So I did this trick, and it was a lot easier to do it this way, especially when the end result is simplified. Okay, so here's what I did. I kept 1/4 as a constant. Then I just did quotient rule of ln of x over x. So again, the denominator squared, which is x squared. Then if you recall, derivative of ln of x is 1 over x times the bottom, which is x, minus derivative of the bottom, which is 1 times the top, ln of x. So the simplified version, x's cancel out. Let me do this. So x's cancel. So you end up with 1/4 times 1 minus ln of x over x squared. And then to take the derivative of this is very similar. 1/4, we keep it as a constant. And again, I did quotient rule. So x squared gave us x to the 4th. Then I took the derivative of the top. Derivative of 1 is 0. Derivative of negative ln of x, that's just negative 1 over x. Then times the bottom, which is just x squared. So notice I canceled them already. Minus derivative of the bottom, which is 2x times the original top, 1 minus ln of x. So just a little bit of simplification. X cancels, so you actually end up with negative 1x, which is negative x. Then I distributed the 2x, so that's minus 2x. And then it's plus 2x ln of x. Notice how x's can combine. Negative x minus 2x will give us negative 3x plus 2x ln of x divided by x to the 4th. And one more step, actually a couple more steps. You can actually notice how there's x here in the first term, second term, and the bottom. We can actually pull that out, cancel it with the denominator. So what we end up with at the very end, you can multiply by 1/4. So notice how there's a 4 in denominator. So this is the final answer. And this is how you would do it. Again, if you just work it out for yourself without looking at the notes, or maybe work it out on the homework by looking at the notes, then you'll see it. Okay, so f double prime of 0 is not defined, because not only because of denominator, but also ln of 0 is not defined. The 2, I plugged in the 2 and I actually put it in the calculator. Just be careful, make sure put parentheses. I actually did the denominator first, so put the top in parentheses divided by 32, and I got 0.050 as the result. That's it for this video, so stay tuned for the second part.